When a reaction reaches equilibrium, it wants to stay at equilibrium. Equilibrium, again, is the rate of the forward reaction equals the rate of the reverse reaction. Our concentrations aren't changing anymore. We can write what are called equilibrium constant expressions. So if I have A plus B yielding C plus D, and this is super, super simplified here, I can write this equilibrium constant expression that looks like this. The concentration of C times the concentration of D over the concentration of A times the concentration of B. So my products over my reactants. So at equilibrium, this is a constant, which means this number cannot change. All right? Which means that if I change anything about this, if I change the amount of C, the rest of the reaction has to adjust to get back to the equilibrium state, to get back to this ratio equaling whatever the equilibrium constant is. So if I stress my system, the rest of my system has to react in a way to relieve that stress and get back to equilibrium. And that's Le Chatelier's principle. Okay, so Le Chatelier's principle says if a stress is applied to a reaction mixture at equilibrium, the reaction occurs in the direction that relieves stress. So if I increase the concentration of something, if I flood my system with more of something, then my system has to react to consume some of that. If I pull out something and I decrease the concentration, then my system will have to react in a way that I can produce some of it back again. Okay? So here I have a reaction at equilibrium, okay? So I have two terms here. You can see I have Q and K. Q is what we call the reaction quotient. And it actually looks exactly the same as the equilibrium constant expression. But what we're looking at is the ratio of products to reactants at any given point in the reaction. Okay, so it's our ratio all right. Now, the other one is K. This is our equilibrium constant. Okay, so this is the ratio to reactants at equilibrium. So what's happening here is I start off there in that gray bar at equilibrium, Q equals K. Because if I'm at equilibrium, my ratio of products to reactants should equal my equilibrium constant. I do a stressor, okay? What I have done is I've added some more chlorine. I've added some more of one of my reactants. So what needs to happen is now my system needs to shift to do something about that. So I added excess chlorine. I added an excess reactant. So if I put in too much reactant, now my system is going to need to form more product. It's going to need to shift toward products or shift to the right in order to consume that excess reactant and get back to that equilibrium state, get back to where Q is equal to K. Okay. When I look at a catalyst, all my catalyst does is increases the rate of the reaction, giving me that lower energy pathway. Both my forward and my reverse reactions speed up. This isn't going to change the equilibrium. Okay, so the equilibrium is not affected by a catalyst. It just means it's going to reach that faster. When I look at equilibrium and volume, okay, this is only applicable when gases are present. Okay, because gases expand to fill their containers. And so gases are going to react differently when I mess with the volume. Okay. And so what happens if I have a lower pressure, i.e. a higher volume, I'm going to shift toward more moles of gas. Okay. So shift toward. Okay. If I decrease the volume, I'm going to shift toward fewer moles of gas. So if I have a bigger volume, I want more gas. If I have a smaller volume, I want less gas. All right. When I look at my equilibrium and my temperature, okay, my rate increases and my shift depends on exothermic or endothermic reactions. Okay, so if I'm exothermic, adding heat is going to do one thing. If I'm endothermic, adding heat is going to do a different thing. All right. So when I look at these and I predict the direction of my reaction, okay, if I increase my concentration of reactant, I'm going to shift toward product. If I decrease my concentration of reactant, then I need to make more reactant, and I'm going to shift toward my reactant. If I increase the concentration of a product, then I need to get rid of some of that, so I'll shift toward reactant. If I decrease the amount of product, then I need to make more product, and I'm going to shift toward the formation of the product. Okay? And then if I look at pressure or volume, if I decrease the volume, I'm going to shift toward less gas. If I increase the volume, I'm going to shift toward more gas. And then temperature, it depends on if it's exothermic or endothermic. All right, so let's take a look at a couple examples. Okay, so here I have an example. We want to know which direction everything shifts when these things occur. So if I add more nitrogen, nitrogen is a reactant. So I'm going to increase the concentration of a reactant, which means I need to consume reactant. So I am going to shift toward products. Okay. All right, what happens if I increase the amount of ammonia? Well, if you look at the reaction, my ammonia is a product. So if I increase the amount of product, now I have to shift back toward reactants because I need to consume some of that. So this is going to be reactants. All right. Now, what if I decrease some of that hydrogen gas? So hydrogen is a reactant. So if I decrease the amount of hydrogen, I need to form more reactant. So I'm going to shift toward reactants. All right, and then ammonia again. What happens if I decrease it? Well, it's a product. All right, so if I decrease the amount of product, then I need to form more product. So I'm going to shift toward products. Okay. All right, now let's look at one with some heat involved. All right, so this is an endothermic reaction. Heat is a reactant. Okay, and so I've written this with heat as a reactant. So what happens if I raise the temperature? If I'm adding heat in and heat's a reactant, what I'm doing is I'm adding more reactant. So what I'm going to do is I'm going to shift toward products. All right, what happens if I take away oxygen gas? Well, oxygen gas is a reactant, so I need to form more reactants, so I will shift toward reactants. What about ozone? Ozone's a product. So what happens if I add in excess ozone? Think about that. Or am I going to shift? Well, if I'm adding in excess product, I have to shift back toward reactants. All right, and then volume. Okay, so remember, when volume is increased, we shift toward more moles of gas. All right, so let's take a look here. On my reactant side, I have 3 moles of oxygen. On my product side, I have 2 moles of ozone. So what's more, 3 moles of oxygen or 2 moles of ozone? Well, 3 is greater than 2, so I'm going to shift toward reactants because that's where I have more moles of gas. So in this reaction, we're going to shift toward reactants. Okay, so that's Le Chatelier's principle. If I stress my system, I have to do something, or my system has to do something to relieve that stress and get back to that equilibrium condition where I keep that constant ratio of my products to my reactants.